Dear students, in first video we discussed the drawbacks of the previous methods and advantages of this state space analysis. In this video, we design a state model for linear system. For this, consider multiple input and multiple output nth order system like this. This is the multiple input and multiple output nth order system because inputs are m, outputs are p, and n state variables. Therefore, the number of inputs is equal to m, number of outputs is equal to p. The system order is n, so that n different state variables will be there. The inputs, state variables, and outputs can be represented as the vector forms like this. So the first vector is input vector having the order m into 1. This vector is state variable vector having the order n into 1. This vector is output vector order p into 1 respectively. These state variables are represented first order differential equation form as first state variable x1 of t can be represented as one time derivative of x1 of t, that is d by dt of x1 of t can be represented as x1 dot of t is the functions of two variables that are state variables and input variables. Similarly, x2 dot of t and so on xn dot of t, where f1, f2 and so on fn are called as functional operators. These functions can be represented as state variables like x1 dot of t is equal to a11 into x1 plus a12 into x2 and so on, where a11 is the constant, x1 is the variable. This is the combination of input u1, u2 and so on um and the state variables x1, x2 and so on xn. Similarly, x2 dot of t and so on xn dot of t. So finally, this format can be represented in simple way as a and b are the constants, so that a ij and b ij are the constants. This can be represented like this: x dot of t is equal to a into x of t plus b into u of t. So where x of t is equal to state vector matrix of order n into 1, u of t is nothing but input vector matrix of order m into 1, and a is nothing but state matrix or evolution matrix of order n into n, and b is nothing but input matrix or control matrix of order n into m. This is regarding state variable equations. And similarly, the output equations are y1 of t is equal to c11 into x1 of t plus and so on, d11 into u1 of t plus and so on. So finally, yp of t is equal to cp1 into x1 of t plus and so on like this. These are also having constant and variables. C11, C1n like this are called as constants. X1 of t and so on u1 of t are called as variables. This also can be represented in single statement or single format as y of t is equal to c into x of t plus d into u of t. This is second equation, where y of t is equal to output vector matrix of order p into 1, c is equal to output matrix or observation matrix of order p into m, and d is nothing but direct transmission matrix of order p into m. So finally, the state model is nothing but the combination of these two equations is nothing but state model. The first equation is nothing but x dot of t is equal to a into x of t plus b into u of t. This equation is called as state equation. Second equation is nothing but y of t is equal to c into x of t plus d into u of t. This equation is nothing but output equation. Combining of these two equations is called as state model of a given time invariant system. These two equations for time invariant system. If the given system is time varying, these two equations can be modified like this. So x dot of t is equal to a of t into x of t plus b of t into u of t, where a is also the time with respect to time, b matrix also with respect to time, c and d matrix also with respect to time. Then the system is called as linear time varying system. So the equations finally can be modified as x dot of t is equal to a of t into x of t plus b of t into u of t, and y of t is equal to c of t into x of t plus d of t into u of t. So these two equations for time varying systems and previous two equations for time invariant system. These are equations for multiple input and multiple output systems. For example, if the given system is single input or single input and single output system, then these equations, how can these equations are modified? So single input and single output means input is 1, output is 1, where m is nothing but number of inputs, p is nothing but number of outputs. Single input and single output means m is equal to 1 and p is equal to 1. The system is also nth order system, so that n differential equations or n state variables will be there. Therefore, the equations are x dot of t is equal to a into x of t plus b into u of t, y of t is equal to c into x of t plus d into u of t. There is no difference in this format, but only the difference is order of the matrix, where a is equal to n into n matrix, b is nothing but n into 1 matrix, because so m is equal to 1 and b is equal to 1, c is equal to 1 into n matrix, and d is equal to constant matrix. So this is the order of the matrix for single input and single output systems. And u of t is nothing but single scalar input variable. So finally, the matrix orders can be represented as like this. So total 4 matrix will be there: A, B, C, D, where A is nothing but evaluation matrix of order n into n, B is nothing but control matrix of order n into m, C is nothing but observation matrix of order p into n, D is nothing but transmission matrix of order p into m, where n is nothing but order of the system or number of state variables, m is nothing but number of inputs for a given system, p is nothing but number of outputs for a given system. If you know this order of the matrix A, B, C, D, we can design any state vector or any state space analysis for a given system. Finally, we can remember this matrix orders, then we can derive any state space model for given system, where A is nothing but evaluation matrix of order n into n, B is nothing but control matrix of order n into m, C is nothing but observation matrix of order p into n, D is nothing but transmission matrix p into m.